Chapter 9, Section 6 is about tessellations. So by the end of this lesson, you should be able to use transformations to draw tessellations and identify regular and semi-regular tessellations and figures that will tessellate. We're going to use all of our transformations tomorrow in class to draw our tessellations. So we're going to do it with reflections, rotations, and translations. So let's warm up for that. A pattern has translation symmetry if it can be translated along a vector so that the image coincides with the pre-image. So I can just slide it and it matches up. A frieze pattern is a pattern that has translation symmetry along a line. So both of these things right here are frieze patterns that have translation symmetry. So you can think about like each one of these ducks. It just gets slid over and then it repeats. It's the same duck over and over again, just translated along a vector. And the same thing with this weird shape. This part right here is the same thing, just slid over on both the top and the bottom. Now the awesome thing about this piece of art is that this and this are glide reflections of each other. So that means if I draw my line of reflection, I reflected this first one over and then slid it up. So it has the reflection and the translation in there. So identify the symmetry in each wallpaper border pattern. So this first music note is exactly like this next one, which is exactly like this next one, which is exactly like the next one, on and on. I'm just taking one picture and sliding it over and over again. So this has translation symmetry. Now these paw prints, we can kind of group them up together like this, slide them over, we get the same set of paw prints over and over again. So this one has translation symmetry and so does this one. But then the awesome thing about these paw prints is it also has glide reflection symmetry as well. If I take this guy and reflect him and slide him up, I end up with that one. Take this guy, reflect him, slide him down, I end up with this one. So both of these pictures have translation symmetry, but this one has glide reflection symmetry as well. So a tessellation, the heart of today's lesson. Tessellations are also called tiling. But it's basically a repeating pattern that completely covers a surface with no gaps or overlaps. The measures of all the angles that meet at each vertex must add up to 360. So in this tessellation that we have here, it's just a wacky quadrilateral. So it has 4 sides to it. And each one of these colors represents the measure of one of the angles. So I don't know what it is, but I know a quadrilateral has to add up to 360. So blue, green, red, and yellow add up to 360. And then when we look how this is patterned, blue, green, red, and yellow all meet up at each one of these vertexes. So that's what this is saying here. Because a quadrilateral adds up to 360, any quadrilateral can be used to tessellate a plane. 4 copies of the quadrilateral must meet at each vertex. So obviously a regular plain old square will tessellate. You see this in tiles all the time. Each one of these are 90, so they all add up to 360. But absolutely any quadrilateral will do that also, because angle 1, angle 2, angle 3, and angle 4 all have to add up to 360, so I could somehow translate that to fill up a whole space. Triangles are also special because we know the angles of a triangle add up to 180. If we put triangles together, we end up with a nice tessellating pattern. So again, take a look at your colors that we have here. Angles 1, 2, and 3 have to add up to 180. So that's yellow, blue, and red. So if you look on each one of these vertexes here where they all cross, you have 2 reds, 2 blues, and 2 yellows. So that's 2 of this, which makes 360 degrees. So 6 copies of a triangle meet at each vertex, and we know that that has to add up to 300. There are two types of tessellations. A regular tessellation is formed by congruent regular polygons. So congruent means they all have to be equal sizes. Regular means that they need congruent sides and congruent angles. So a square works. You need all 90-degree angles, all nice even sides. An equilateral triangle would work, everything equal. A regular pentagon where all the angles are congruent and all the sides are congruent. Those can make a regular tessellation. A semi-regular tessellation is formed with two or more different regular polygons with the same number of each polygon occurring in the same order at every vertex. So what the heck does that mean? If we take a look at this first one here, where it's all the blue triangles, this is a regular tessellation because you have an equilateral triangle that just is moved around and makes this nice pretty shape. It's one shape that makes it. Where this one is made up of squares and triangles. All of these have to be regular, and if you look at each vertex, the same thing makes up each vertex. You have two yellows, two blues, and a green. So you have three triangles and two squares. And they have to appear in the same order. So if we start this as like our one, it goes square, triangle, triangle. And then if we look here, if we start there and work our way around, it goes square, triangle, triangle. Same order. So you'll be asked questions like this. Classify each tessellation as regular, semi-regular, or neither. So the easiest is going to be this one in the middle. It's all the same triangle, even though it's different colors. This is a regular tessellation. Now this first one here, it's important to know that even though this is using the same shape over and over, this is not a regular shape. These sides are not all the same. We can tell that clearly by looking at it. So that means that this can't be regular or semi-regular, it's neither. Where this one here, if we take a look at each vertex, you have a square, triangle, square, and then a hexagon, square, triangle, square, hexagon. And it works at every single thing that we have here. So we're using three shapes. They're all regular shapes, but they appear in the same order. So this is semi-regular. So will these polygons tessellate? Determine whether the given regular polygons can be used to form a tessellation. If so, draw the tessellation. So we're assuming that these are regular, equal sides and equal angles. So because this is a triangle, what we need to look at is how many degrees are in a triangle. So we know there's a total of 180. That means that each angle has 60 degrees. So is there a way for 60 to fit into 360? Because remember, they have to make that 360 degrees so there's no gaps or overlaps. So 360 divided by 60 means that we need 6 triangles together to make a tessellation. And we've seen this picture a few times, but if we were to draw it, it would look like this. We keep going all day long with this, and then even if we wanted to put one on top of here, we draw it like this so that we could have a backwards one there and then another one there. Now these shapes here, we have a regular pentagon and a regular triangle. So we already know that each angle here is 60 degrees. And now in a pentagon, we have to figure out the interior angles and how many angles are in each one. So think back to chapter 6. We learned this formula. N is the number of sides, so we have 5. Take away 2, you end up with 3. And if I multiply 3 times 180, I end up with 540. And then if I divide that by 5, just like I did over here, that tells me that there are 108 degrees in each one of these angles. 108. So is there a way that I can do some combination of 108 and 60 to add up to 360 degrees? So start thinking about this. We know if we have a couple of 60s, our multiples are going to be 60, 120, 180, 240, 300, and 360. There is no way that I could add one of these or two of these or anything to any of these things here in order to add up to 360. There's no combination because our multiples of this are going to be 108, 216, and then after that it's 324. So there's no combination of triangles and pentagons that I can use that add up to 360. So these will not tessellate. So you should be able to use transformations to draw tessellations and identify regular and semi-regular tessellations and figures that will tessellate. Write down any questions you have and we can go over them in class. Enjoy your night.